Now, for the last part of this lecture, we're going to turn our attention to three-phase. First question I'm going to ask, why three-phase? Well, the reason for this goes back to Nikola Tesla. From my perspective, he invented the three-phase induction motor. That's well known. That, in my opinion, is the greatest invention of all time. And I could probably argue this with anyone if they wanted to argue it with me. The reason being is that the three-phase induction motor enabled the use of electrical power to drive industry. So industry requires movement and motion, constant motion. You've got pumps, roller mills, you've got things that are spinning, things that are turning. You need to have rotational motion, and it was a three-phase induction motor that made it possible to achieve motion directly off of an electrical line in its native form coming from a three-phase generator or a synchronous generator, as opposed to DC power, which is what was competing against Nikola Tesla's ideas, which required a lot of extra junk to actually make things work and convert the mechanical energy into electrical energy. Now, this will be probably clear to you by the time we're done with this class and we've gone through the induction motor and synchronous machines. But electromechanical energy conversion is the conversion, as I said at the very beginning of the class, of mechanical energy into electrical energy. And in order to get there, it has to utilize a stored magnetic energy, which is the main subject of this class. So it also goes in the reverse direction. You have electrical energy that could be converted to mechanical energy, thus the three-phase induction motor. So the synchronous generator was mechanical to electrical energy. The motor is electrical to mechanical energy. Three-phase is the most effective way to implement the magnetic circuits that make this happen, because it results in the most effective utilization of the copper and iron. It results in the most simple motor structures, and as I said, structures that can be powered directly from the three-phase power without any intervening mechanisms whatsoever. In our world today, we have electronic circuits that can intervene and shape the power and make it do whatever we want it to do. Back in the days of Tesla and Edison, you had to do that shaping through a lot of mechanical, electrical, magnetic intervention, some of which you will learn about in this class. Now, for transformers, and what is a transformer? We will talk about them, but most of you know a transformer converts AC voltage from one voltage level to another. And the transformer, if it is a three-phase transformer, you will have the most effective utilization of the copper and iron. It'll be the smallest and the lightest possible implementation. And now what about distribution of power? Three-phase is extremely useful there because it enables a great flexibility in how you will be distributing this power and how you will protect against events such as short circuit faults and damage. So three-phase power means this. Electrical power must first be generated from a three-wire system or a three-phase system that has a common reference for a voltage measured from each wire to that common reference. We refer to that reference as a neutral. And the other end of three-phase power would be three wires that connect to those three lines. I'd like to start in our understanding of three-phase again with the scalar periodic functions for voltages. And I'm going to show how we can reflect these scalar representations onto an axis or multiple axes through the use of a rotating phase vector, or the phasor, the time variant phasor to be exact. So this is really where it all comes together. So let's get started with this. Remember, we talked about creating a scalar periodic function for a voltage that would be repeating sinusoidally, so it looks like down here, I'm going to circle, we're actually going to talk about three of these voltages. And let's start with the first one. So what I'm talking about right now is that voltage. And this is the exact same equation that we showed before, with one small variation. Instead of calling this, we called it before VRMS. And now I'm going to call it V phase RMS, the RMS voltage of the phase voltage, for a reason that we will make very clear as we proceed. Now what you could do, in the same way that we showed with a voltage and a current, and we were able to displace the current from the voltage by an angle, we can do the same with another voltage. So we could say I've got another voltage. We're going to call this VB. So we have a voltage, the first one, which we were calling V alpha before, I'm calling VA. The second one I'm going to call VB. And I have a third voltage, VC. This is VB. Which of these three waveforms do we think is VB? We'll recall again that this x-axis here, if we say that is omega t or omega e times t, it's the same as saying an angle theta e. There's theta e right there. And if I look at this VB of t, it tells me that I'm going to get a cosine of 0, which will mean that I'm going to hit my peak voltage right here when theta e equals 120 degrees. When theta e minus 120 is equal to 0, I'm going to hit another peak. So I'm going to move out here, and this is that point right here. So there's 120 degrees. I hit another peak. This bottom waveform, the red one, is VC. And notice it has a plus 120 degrees. And what it means is that theta e equals negative 120 degrees VC of negative 120 degrees is going to be equal to the V peak, which is square root of 2 times V phase RMS. Now this one is a little tricky. You say, well, I'm moving along in time. You're saying this is the beginning of my time reference right here. So how can I become negative? Well, we can think of, here is where the the repetitive periodic function helps us out. So we know that if we were to take 120 degrees and add 120 degrees to it, and then add another 120 degrees to it, we would get 360 degrees. So that would put us, if we said this is 0 degrees, this is 120 degrees, this would be adding the next 120, that would be 240 degrees, and then this point right here would add the other 120, that would be 360 degrees. So there's a really great symmetry here, because what's happened is when I get to the 360 degree point, my A phase is starting over again at its peak. In fact, everybody's starting over where they started out. It's repeating, because that's really one period. And when we were talking about this before, we were saying that we had a repetitive period of 2 pi radians, right? And from that we were able to come up with this angular frequency, which is 2 pi times the electrical repetitive frequency of the sine wave. From that you actually would get the angle, because the angle could be the integral of that angular speed, which is omega e t. So you really just have this little factor that you decide if you're going to put that, multiply it times t to create the increments of your x-axis, then it becomes an angle, otherwise it's a time. So if we didn't have this, if we just had t, then this period would be big T, and Fe is 1 over t. So I am being a little bit overly detailed, I guess, on this, but want to make sure this is clear to everybody. So we know that when we get to a full period, and we can definitely see this in this polar representation of everything up here. Let's consider that we have a phase angle. Let's consider that we have a phasor. The phasor is rotating. The phasor is rotating at a constant speed of omega e. This point right here, if I'm starting right here, that is theta e equals 0. And I go all the way around and I get to theta e equals 360 degrees. So what's happened is that I've completed my rotation and I'm starting it over. So, 0 degrees equals 360 degrees. So that means that I'm going to be able to, if I want to, I'm going to come back to the C voltage and this angle right here, and when do I hit my peak? I have a peak here that is at theta E equals negative 120. I'm going to hit that peak again right here. This is 360 degrees later as far as the amount of angular travel that has occurred since I was at my last VC peak. So if I've got a 360 here between the peaks, and there's a 120 degrees between the peak of the C phase and the zero reference point here. So if I want to take the difference between these two angles, I'm really taking the difference between this, and I'm trying to say, well, I want to find out what is the angular space here. So 360 degrees minus 120 degrees is 240 degrees. So that tells me that I could even replace this whole thing here with minus 240 degrees. So that would mean that when the angle hits 240 degrees here, positive 240 degrees, I am going to get a zero inside of this these parentheses after the cosine, and I'm going to hit the C phase peak. Okay, so returning to what we just discussed, let's talk about the A phase again, and let's just consider that phase by itself. The A phase is this blue line right here, and what I'm going to do is I'm going to superimpose a axis on top of this polar coordinate system. It's really like the x-axis of a Cartesian coordinate system. And we showed that if we have a phasor here that's mathematically represented as the rotating phasor, the real part of square root of 2 times a stationary complex phasor that has the RMS amplitude in the phase times ej omega t, which is the time variant part of that this phasor is moving at this angular velocity of omega e. And as this phasor moves around, it's going to reflect onto this axis A. So the point in time, at any point in time, if I freeze this phasor and I take a cosine of the angle that I am at, cosine of my theta e point, multiply it times whatever the v peak is, I will get the corresponding V at the t corresponding to that point, the point in time, recognizing that t is theta e divided by the angular frequency. So plug that into there. This is VA of t. That would mean that I'm going to plug that into here, and I would get a scalar voltage that would be this point. And that would be the VA value. Okay, now what about the VB phase? So the VB phase is represented by, it looks like this is a black line right here. That's the periodic scalar function VB of t. Now recall when we were introducing scalar periodic functions for the first time, and this alpha axis, which we're now calling an a-axis, and we introduced a beta axis, and we had a voltage that we called V beta of t equals square root of 2 VRMS sine of omega et. Now that would have been the same thing as saying square root of 2 VRMS cosine omega et minus 90 degrees. These are equivalent. And we said, well, we're going to introduce this other axis just in case we want to use the sine instead of the cosine. And so we could have, with the same phasor right here that's moving at this angular speed, we could be reflecting that phasor onto the beta axis, and it would produce the sine wave, not the cosine wave. So what we're going to do is we're going to extend this concept to three-phase voltages, except in this case we will have three separate periodic voltages, just as we're showing down here, that are existing together all at the same time. And we will be able to produce the respective periodic scalars for each of the three-phase voltages by reflecting this phasor here onto the respective axis. That's how you can envision synthesizing periodic scalar functions, and you could envision finding instantaneous values and understanding the concepts of leading and lagging currents in associated circuits like we had talked about before much easier using the polar coordinate frame. So a time variant phasor representation of the voltage can be very useful and very insightful. We could therefore take this beta axis and move it, rotate it. It doesn't have to be at 90 degrees off of the alpha axis as we had it before. Now we're calling an a-axis. But what we've just done is we have displaced that axis by 120 degrees. And now we can envision that as this phasor moves along, it would reflect onto this axis here and produce this voltage VB. So we're this angular position that we're at right here. Let me try to get this to work. I'm going to move it around a little bit. So we're up at another position right here because it's a little easier to see what's going on. I've got here I'm at theta E equals 90 degrees. Now where is that on this Cartesian reference frame here? That would be right here. We know that the VA would be equal to 0, and we can tell that the VB, which is this waveform right here, is almost at its peak at that point at 90 degrees. If we look at this mathematically, what we're saying is that we're at a position, an angular position of omega ET equals theta E equals 90 degrees. That's the same as square root of 2 V phase RMS cosine of negative 30 degrees. Now the calculation of what the instantaneous value of VB is at that position would be square root of 2 V phase RMS times square root of 3 over 2. That's what the cosine of 30 is. So this is about 0.866, so we're about almost 90% of the peak. That's definitely what we see down here, reflecting that onto that point. We can see that as well. This angle here is actually 30 degrees. So you can see how useful this is, understanding three-phase from this perspective. Now what about the C-phase? The C-phase is represented by this red signal down here, and we could look at our phasor representation here and the superimposed axes, and let's observe something. The phase shift of VB of t off of 0 is 120 degrees. The phase shift of VC t is 240 degrees. So that's an additional 120 degree shift. So let's take this axis that we had on the V lined up, and we called this the VB axis. And again, just to point out, everything in this direction, starting from this point here, going along that line, is positive, and everything going along the line here is VB t less than 0. So you can imagine that the voltage is going between these points, just moving as the phasor moves. Okay, so I'm going to move this phasor, this axis, or put a new axis on that is another, it's 240 degrees. This axis is 240 degrees away from our theta E equals 0 point. And on this axis, everything positive this is your origin, is in this direction, and everything negative is in that direction. And we could say, okay, let's go back and look at that 90-degree point right here. Look at all three of these voltages. They're happening at the same time they're hitting 90 degrees. So we know that VA is at 0. We know that the VB is at 0.866 times the peak voltage. VC at theta E equals 90 degrees. And what I've done, that means that this phasor has moved to that point right there. VC at 90 degrees, square root of 2 V phase RMS cosine of 90 minus 240. So that would be negative 150 degrees. Now what is the cosine of negative 150? Here's the point I want to just a little bit of trig to remind you. Cosine of 180 is equal to negative 1. Cosine of negative 180 degrees is also equal to negative 1. So if we have if theta E is greater than 180, we're going to get negative amplitudes. Less than negative 180, what are we going to get? Let's think about that for a moment, and let's look at the angle along this omega ET or axis, thinking of it as an angle now. If this is a 0, and look at our VA, we had VA was at 180 degrees, it's negative. At negative 150, it's also a negative number. So we know from this, and we can see that a cosine of theta E less than negative 180 is also negative. But if we look at the phasor, and let's reflect that phasor onto the c-axis, we are on the negative part of the c-axis. So at that point we will be at square root of 2 V phase RMS times negative 0.866. So looking at this waveform down here, we're at the 90-degree point. We are actually at the same amplitude on the C phase as we are on the B phase. It just has an opposite sign. So the B phase was coming up on its peak, and the C phase just went past its negative peak. Definitely we can see that. So if we're looking at the phasor here, phasor's moving in this direction. When it hits that point, it's at its negative peak, and then when it goes over to here, it's on the downside of the negative peak, going down. As far as the B phase goes, coming up here at 90 degrees, and then it's going to hit its positive peak and then start going downwards towards 0, which would be right about there. That would be the point at which we're lining up with the 0 point on the B axis. And I'm not going to belabor this anymore after this, but essentially considering what's happening on the C phase at the same time as what's happening on the B phase, we're moving as the phasor moves back and forth along the C axis. We're moving as the phasor moves back and forth along the A axis. Mathematically, we have scalar representations of the periodic functions VA of t just as we had shown before would be we can look at the phasor mathematically as this function square root of 2 times a phasor, which I'm going to identify in this way as a phasor of VA, E j omega E t. VB of t square root of 2 V phase RMS cosine omega E t minus 120 degrees. The phasor, time variant phasor, square root of 2 times a stationary complex phasor that we will define as VB, and the periodic scalar representation of VC has a phase shift of 240 degrees. The mathematical representation of the time variant phasor, square root of 2 times a stationary complex phasor VC times the rotating part here. Okay, so now I've actually gone into this aspect of phasors and scalars in a little more detail than maybe is needed, but hopefully some of you will appreciate the insights. What is important and what you need to remember now going forward are these three things here. These phasors. We're going to again go to the stationary or time invariant phasor representations and use them. What are they? The three complex phasors, VA, VB, and VC, are represented this way. I'll let the interested student derive those if you wish. This isn't something that, again, you will be tested on or that is important as far as the base knowledge of this course. It's to give you some insight. But we're right here now almost at the point where we really need to start paying attention here to what I'm doing. But I've spent a little bit of time to answer the why and why we ended up here. And I think that if an interested student is going on into power systems analysis, power electronics, there will be a lot of good insight that can be carried forward from this analysis into those fields. I want to make another thing though clear to everyone very briefly. So if we have a phasor VB equal to V phase RMS negative 120 degrees, if we were to write this as V phase RMS 240 degrees, that's the same thing because of the 120 degree symmetry. Also, if we say VC is V phase RMS positive 120 degrees, we can write it also as V phase RMS negative 240 degrees if we want it. So it's really up to us how we want to represent these phasors. Notice also that I'm writing these in degrees, not radians. So to convert from degrees to radians, you would say, let's say I've got 120 degrees. Pi radians is the same as 180 degrees. So here's a conversion over to radians. What I'm going to end up with is 2 pi thirds. So 2 pi thirds and 120 degrees are the same thing. 4 pi thirds and 240 degrees are the same thing. So you could write these expressions this way as well. Okay, so just to make that little clarification, because I've been going back and forth between degrees and radians. So what we have is we now have come up with three phasors representing the voltages in a three-phase system. Those are these three phasors with the little yellow marks on them. You can imagine that these phase voltages could be applied to three separate circuits and get three currents from those circuits: an I phase current, a C phase current, and a B phase current. Three-phase systems are often represented in this way. If we were going to make a circuit diagram from the source side, this would be, for example, the A phase voltage. This would be the B phase voltage, and this is really supposed to represent a 120 shift. This would be a 240 degree shift. This would be the VC voltage. So this is the way the source is represented, and you might maintain the same kind of pattern over at the load side. And what you do with three-phase systems, and what's the most ideal way to apply them, is to balance the load so that you can imagine, as I said before, three separate circuits powered by these three sources. And I'm going to represent points on these lines coming out. This is A, This is B and this is C, points of reference. On the other side, I can make the same points of reference, A, B, and C. And then I can connect them together. Now, I said you have 3 separate circuits, so let's draw the return line. So you've got your phase A voltage applied, and here's the phase A current. You've got your phase B voltage applied, and this is the phase B current. And this one's a little bit weirder the way I'm going to draw it. You've got the phase C voltage, and that's the phase C current. 3 separate circuits represented this way. There is a common point of reference when it comes to voltage at this side and on this side, and that common point of reference is referred to as the neutral. It follows that these 3 points could be connected together. And if we did that, this line here looks a bit weird. We could just make it connected up here instead. And now we've got this neutral line. Since I also have these 3 phasor representations of the circuits, it follows that I could calculate the apparent power just the way that I showed how to do it with the single phase AC circuit, by taking the phase A voltage times the conjugate of the phase A current, adding to it the phase B voltage times the conjugate of the phase B current, and the phase C current, and the phase C voltage times the conjugate of the phase C current. If I do that, since it's a balanced circuit, the IA magnitude equals the IB magnitude equals the IC magnitude, and we know that is what we're calling right here I phase RMS. They all have that same amplitude. Then the total power to the 3-phase circuit, because what I've done is I've connected all of their neutrals together, is 3 times V phase RMS times I phase RMS, scalar quantity here. The power is the S magnitude times the power factor. And the reactive power would be that volt ampere magnitude times the sine of the power factor angle. Since these 3 loads are balanced, they all have the same power factor angle. So with the single phase circuit, recall we had, or we could just say V times I conjugate was S. We could think of this as A three-phase circuit is just 3 times the value of each phase S value. So this would be like the S per phase. So you could have 3 times the S apparent power in one phase. All you really have to worry about when it comes to the power calculations with the three-phase system is this factor of 3. Just don't forget it. Now in the lab, which the second lab that you will do, you will be working with a three-phase circuit like this. And this looks a lot like the sketch that I drew where we had the sources on this end and we have the loads here, and whereas I showed each load having, say, an R and an L, in the phasor representation this would be R JXL. That whole thing right there is the Z that I'm talking about. Now I'm just using this as an example. You could have a much more complicated circuit than that on the inside of whatever this total Z is here. It could be a parallel RL. It could have a capacitor in there even, or multiple branches. So it can be as complicated as you need it to be. I want to point out another thing. If we look at the shape of these 3 voltage sources and the 3 loads, they look like an inverted Y. Well, that's recognizing that this configuration of the source and the load are referred to as Y configurations. Now let's go back to this phasor representation of the 3-phase AC voltages and currents for just a moment. And I want to point something interesting out to you. We have, of course, symmetry, 120 degree symmetry between the phase currents and the phase voltages. I'm going to show you something with a phasor diagram. We're going to use it to figure something out mathematically about this balanced load that we are putting onto our 3-phase source. So I'm going to attempt to grab this vector. I've got my IC vector, IB vector, and I'm going to add them together by connecting, well, let's go in ABC direct. Now I think that my dimensioning of these, which I used my eye to do, wasn't quite right. But what will happen is if you add these 3 currents vectorially together, they actually sum to 0. That's what this phasor is telling me. It's saying go here, add this, and I come back to the origin, and that is a summing of currents to 0. There's a lot of ways we could prove this, and if you want to go off and prove it to yourself, you can. Trigonometry can certainly be used, but the sum of these 3 currents is equal to 0. One of the currents is always going to be dependent on the other two. What I'm looking at here is a three-phase source connected to a Y load, and there are three lines, A, B, and C, that are connected together. In the sketch that I drew, I indicated that these three return lines are all connected together, and that there could be a fourth connection here, a fourth wire connecting the two sides, a neutral wire. So that's shown right here. So this is actually the return line of all three currents. But because the three currents add to 0, so you've got your current IA here, your current IB, and your current IC all going into this point, but they're going to be 0. You can take this line off. You don't even need it. And in the lab, one of the little experiments that you will do is you will set it up as a 4-wire system where you make a neutral connection between the two neutral points in addition to the A, B, and C connections. And what you will see is that there's no difference if you remove the neutral connection. I don't want to go into this in too much detail, but this is only true because of the 120 degree symmetry, which is what you will see in typical three-phase power systems. Power electronics, on the other hand, and this is not a power electronics class, but power electronics introduces what's called common mode current, ICM, which is an instantaneous summing of currents, say scalars at any point in time, that do not equal 0 because of the switching of the transistors in power electronic circuits, and that's what causes your electromagnetic interference. But we don't have any of that here, and we're using these stationary phasors because they each are representing perfect sinusoids. Leaving this idea of common mode is just a little bit of information for you. Let's come back to this circuit, and how would you make measurements on this circuit? Where would you make your measurements? Well, let's look at the lab setup. We have the power meter in the lab. There's a current sensor in each of these lines. L1, that could be what we're calling A phase, L2, B phase, L3, C phase. There's also a possibility in the lab, and you will get to do it, to connect this neutral. The voltage measurements are from each line to neutral. And so what you're seeing is a voltage V line to neutral measurement. You could also make a voltage measurement across two lines. Say that there was a voltage sensor here. Now the power meter synthesizes that voltage from these three voltage measurements, and I'm going to show you how that can be done with phasors in a moment. But voltage measurements line to line would be done in this way. So there's a line A to B, B to C, and C to A. So measuring across all three lines. and these are what we would refer to as line-to-line voltage measurements. You can measure voltage as a line-to-line, or if the neutral is available, which it is in the lab, you can make measurements line to neutral. The current measurements made here are in the line, so typically this is called I line. We've introduced this as a three-phase circuit initially, and we would say that this is a phase current coming out of here, and it definitely is. And we've said that this is a phase voltage here. But the phase voltage and the line to neutral voltage, while they are the same in this situation, may not always be the same thing. That is the key to understanding how to analyze three-phase. Understanding what is the phase voltage, what is the line to neutral voltage, and when they are equal to each other. So we will go into that as we get deeper into three-phase systems. What does the line-to-line look like if we were going to use phasor analysis? The line-to-line voltage is the difference between the line to neutral voltage, which is the phasor shown as VA, and the phasor VB. So the two line to neutral voltages of A and B phases, the difference between them is the line to line phasor voltage. So how would we do this using a phasor diagram? We could come up with mathematically what VAB is through all of this math that I've described right here. But we can easily see what it's going to be if we just look at our phasors here. So I'm saying take VA, that's this phasor here, and subtract VB. So how do you subtract phasors? So here's VB, positive VB. What you would do is you would say VA minus VB is equal to VA plus negative VB. So I'm going to take this phasor here and I'm going to make it a negative VB by moving the arrow to the other side. Okay, so I move the arrow pointing in the other direction. I'm going to take this and I'm going to stick it on the end of VA, and now I have VAB. Where this ends, draw a phasor from the origin to that point, and that would be the result, VAB. Mathematically, what VAB ends up becoming is square root of 3 times the phase voltage RMS value or peak value. This applies with RMS and peaks, but we're using RMS because we're using phasors. There's also a 30-degree phase shift between VA, which is the line to neutral voltage of VA, and VAB, the line to line voltage. So V line to line RMS is equal to square root of 3 times the RMS value of the phase voltage. Well, now let's return to the diagram of a setup in the lab. What I'm showing here, if you'll recall the first diagram that I showed you, this diagram here, had a Y connection of the load where the reference point for each load was connected to the neutral. But I could take this same load and I could connect it a different way. I could connect it this way. This is what's called a delta connection. Instead of connecting each load from the line A, B, C to a neutral point here, which exists over on the load side, I connect each load from A to B, B to C, and C to A. So what happens with a delta circuit? Well, from this circuit diagram we can see that the three currents coming from the source, the three-phase currents, IA, IB, and IC, are coming in, each of them, to a node that connects a path to another phase. If you look at the first node, for example, at this node A, the IA current coming from the source, the line current, is dividing up between the current going through the phase, the AB phase, and the CA phase. It's the vectorial sum, or the phasor sum, of those two currents that make up the line current. So we can look at our phasor diagram and understand a little bit what's going on here. This is a similar situation to the line-to-line voltage calculation, except in this case the phase current from the AB phase and the phase current from the CA phase sum together to make up the line current here. You can go through all the trig and figure out what, obviously the line current ends up being of a greater magnitude than the phase current, I phase RMS, of the two phases, the two balanced phases, and it is more than that phase current by this factor of square root of 3. So this is the last thing I'm going to share in this lecture, and then we will follow up in the next lecture showing how we can use everything we've learned to solve problems. But I want to summarize a few things. The first thing is that we have, in three-phase systems, three voltages displaced by 120 degrees of the electrical angle, which is theta E, looking at it in the scalar phasor, time variant phasor representation. This is a symmetry that brings a lot of advantages, which we will demonstrate. The three-phase voltages have a common point of reference, which is referred to as a neutral connection. And so that would mean that if we have a phasor voltage VA, what that really is it is the voltage from A to neutral. We could write it this way if we wanted: VA to neutral, VB to neutral, VC to neutral. The three voltage sources with the common point of reference are connected together at that reference. So we can imagine the three sources. There's the neutral, there's line A, there's line B, and there is line C. And the three lines coming from a three-phase voltage source connect to either a Y configured load or delta. Sometimes the symbols are used, load. So the load may look like this, or the load may look like this. A fifth point which I want to write here is that the current in the neutral is 0. So what that means is that since this point right here constitutes a return path for all three phases, the three currents that are going out to a load sum to 0 at the source and at the load. So it's not necessary to make this fourth wire connection with these types of loads. If you have a delta connection, you don't even have access to a neutral at the load. If you have a Y, you do have access, and you could connect it if you wanted. That's not necessary in the simple types of systems we're going to show. There are uses for four-wire systems, but that's not something we would go into in this class. The last few points are that you can measure voltage from the line to neutral point on any one of these lines, or from the line to line point. So a line to neutral voltage is VA. Line to line voltage is what we would call VAB, or which is the difference between VA to neutral and VBB to neutral, and so on for all of the phases. We may measure the current in the line coming from the three wires, or if we look at it from the source, from the load end, we can measure the current, and we can measure these voltages the same way as a line current. If we have a load that is connected in a delta, we could also have a phase current measurement where I line does not equal I phase. This is for the delta. There are amplitude relationships between line to line and line to neutral, or line and phase. The line to line voltage in any three-phase system is equal to square root of 3 times the line to neutral voltage. This is the amplitude that we're talking about here. So we could say V line to line RMS is square root of 3 times V line to neutral RMS. In a delta connected load, the line current magnitude is equal to square root of 3 times the phase current magnitude, or I line RMS, square root of 3 times I phase RMS. We will pick up at this point in the next lecture, and we will provide some examples.